So what we were saying is there are two types of exponential equations, basically. There are those where you can rewrite them with the same base on each side, and there are those where you can't. So, for example, here, the first type of equation where you can write the same base on both sides, an example would be 2 to the x equals 8. Since we know 8 is a power of 2, it's 2 cubed, we could rewrite it that way. And then, if 2 to the x is equal to 2 cubed, it has to be that x is equal to 3. And that's because of what's known as the one-to-one property of exponents, which says that you can't raise 2 to two different powers and get the same answer, basically. So we can say then x has to be that exponent 3. So that solves the equation. It gets x out of the exponent, which is what our goal is. This also works if you have two exponential expressions, one on each side. Like let's say you had 5 to the x plus 3 equals 5 to the x minus 9. Okay, well actually let's do 2x minus 9. So that would mean that x plus 3 would have to be equal to 2x minus 9, and then you would solve from there. You could subtract x from both sides. You get x minus 9 equals 3. Add 9 to both sides. You get 12 equals x, and you're done there. So that's the kind of exponential equation we're talking about. But a lot of the time, we can't write both sides with the same base. For example, here we have 5 to the x equals 10. 10 is not a power of 5. It's a multiple of 5. It's 2 times 5, but it's not a power of 5. You can't say it's 5 squared or something like that. So as a result, we can't use the one-to-one property of exponents. So instead, we're going to take the natural log of both sides and use the power rule of logarithms to rewrite it and get the x out of the exponent. So here we're going to take the natural log of the positive number 5 to the x. I know it's positive because when you raise a positive number to a power, you get a positive. And the positive number 10, natural log of 10. So then on the left, we can use the power rule of logarithms, which says that if you have a power on the argument of the log, you can bring it out front and make it a factor without changing the value. So now we have an equation we can solve for x. We're going to divide both sides by natural log of 5, and we get x equals natural log of 10 over natural log of 5, which, by the way, is the only way to write the exact value of the expression. And don't make a common error of thinking that you can simplify this expression. Sometimes people even think the natural log is a variable, and we can just divide natural log by natural log and be left with 10 over 5. And that is most definitely not the case. You cannot simplify any further. Now, if you happen to want an estimation, an approximation of what natural log of 10 over natural log of 5 actually is, you can find that on your calculator. Divide the natural log of 10 by the natural log of 5, and you should get 1.4307 if you go out to 4 decimal places. Okay, so let's try and apply these two ideas. So as we look at these equations, we want to decide, is this a scenario where we can write both sides with the same base or not, in which case we're going to just take the natural log of both sides. So let's start with part A. Maybe zoom in a little bit. Okay, we have 9 to the x plus 1/2 power equals 27. And so what you want to be thinking about is, can 9 and 27 be written as powers of the same base? Well, I know 9 is 3 squared. Is 27 a power of 3? Yes, it is, because it's 3 times 3, which is 9, times 3 again, that would give you 27. So 27 is also 3 to a power. So what we're going to do is replace each base with the exponential expression that it's equivalent to. So instead of 9, I'm going to write 3 squared, and then I'm going to have to the x plus 1/2 power. And instead of 27, I'm going to write 3 cubed. Now, you do need to know your rules of logarithms. rules of exponents. For example, here we're raising a power to a power, so we have to multiply the exponent. So I'm going to have 3 to the power of 2 times x plus 1/2 equals 3 cubed. Now that we have 3 to a power equals 3 to a power, we can use the one-to-one property of exponents and just say, well, those powers must be the same number. And then we're going to go ahead and solve. So from here, 2 times x is 2x, 2 times 1/2 is 1, 2x plus 1 equals 3. Now solve for x the way you would in any normal, regular old linear equation. So we're going to just isolate the variable by subtracting 1. So 2x is equal to 2 and dividing by 2, and we get x equals 1. Now let's suppose that we wanted to check our solution. It's not mandatory in this type of problem, but it is not a bad thing to do. So we would plug x equals 1 into the original equation, which was 9 to the x plus 1/2 equals 27, and we'll see if we get a true statement. So 9 to the 1 plus 1/2 equals 27. Is that true? Well, that's 9 to the 3/2. Well, remember, 3/2 power means square root of 9 cubed, which is 3 cubed, which is equal to 27. So yeah, that actually does check out. So x is equal to 1. Okay, if you're just joining us, I know we've had some technical problems. I'm sorry about that. We're solving exponential equations, and one way to do that is to get the same base on both sides and set the powers equal to each other. So that's what we're working on now. All right, here's another one. Can we get the same base on both sides? Well, we kind of already do have the same base, but the only problem is that this base on the right is actually in the denominator of the exponent. Of the fraction. We can't have that. So what are we going to do? Well, remember, we had a rule that said if you have 1 over b to a negative power, you can flip that to the top and make it b to the positive version of the power. So we're going to do that, or I guess I should say, if you have 1 over b to a positive power, you can flip it up to the top and make it negative. Either way. All right, so in this case, which one do we have? We have 1 over e to some power. I don't know if 2x is positive or negative, but it doesn't matter. We just take the opposite. So we have e to the x plus 4 equals e to the opposite of 2x. All right, so now we have the same base. Remember, e, by the way, is just about 2.7, but it's an irrational number like pi, so we can't write it out in decimal form. It goes on forever, so we just write e. All right, so, but when we raise that number to the x plus 4, we get the same result as when we raise it to the negative 2x. So that must mean that x plus 4 is equal to negative 2x by the one-to-one property of exponents. So now we're going to just get x by itself, because we've accomplished a lot here. We now have x out of the exponent. That's really our goal, because from there we can apply other techniques of equation solving. Since this is a linear equation, I can subtract x from both sides, so we get 4 equals negative 3x. And then we're going to divide both sides by negative 3. So we get x equals negative 4/3. And again, you could plug in to check, but for the sake of time, we're going to continue on. All right, now we have a different scenario altogether. We have 10 to the x equals 8.07. Definitely no way we're going to be able to write both sides with the same base. I can't write 8.07 as 10 to a power, and 10 isn't something else to a power either. So we're going to have to use the other method. So when you can't write both sides with the same base, what do? You take the natural log of both sides. So we're going to take the natural log of 10 to the x is equal to the natural log of 8.07. Okay, and this is still going to allow us to get the x out of the exponent, taking the log of both sides. So using the power rule of logarithms, we can bring this x out front. And that's how it gets out of the exponent. So we have x times the natural log of 10 equals the natural log of 8.07. Oh, and I do want to remind you, in the instructions, it will generally tell you either to find an exact solution or write an exact solution in terms of natural logs and then approximate it to a certain number of decimal places. So what I'm going to do next here, oops, where did I go? Too far. Okay, so what I'm going to do next is get x by itself by dividing both sides by this natural log of 10. But when I do that, the exact solution written in terms of natural logs is just what we see here. The natural log of 8.07 divided by the natural log of 10. We really don't need the parentheses there. You can write them, but it's not necessary. Okay, so this is your exact solution. And a lot of times people get confused. They think that this can't possibly be the exact solution, that it has to look like a decimal, but that's just not true. This is the only way to write it exactly. And then you can approximate it, and we were asked to do so in this problem to 2 decimal places by plugging it into a calculator. Not sure why my OneNote is disappearing. Let's see. Okay, so we have 8.07. We're going to take the natural log of that, and then we're going to divide that by the natural log of 10. And that should be about 0.91. So check on your calculator, make sure that you can get that same result. Okay. And by the way, you should also be able to check if 10 to the 0.91 is approximately 8.07. It should be a little off because we rounded off our answer, but we can see if we're in the right ballpark. So let's check that. Is 10 to the power of 0.91, what does that equal to? 8.13 is what we got. See, rounding off to the 0.91, we're off by that amount, but that's okay. This is an approximate solution. That's why the other one is the exact solution. Okay, let's keep going. But remember, if you have any questions, you can type them into the chat bar. Okay, let's look at this one. Same instructions. But we have a little more work to do here because remember, you have to be able to isolate the exponential expression. So when I say exponential expression, I'm talking about this thing right here. And to isolate it means get it by itself. So we're going to start by subtracting 1 from both sides. So we have 2 times 3 to the x over 7 equals 0.4. You cannot multiply 2 times 3 here and get 6 to the x over 7, by the way, because 2 is not being raised to the x over 7 power, only the 3 is. So that's okay. We're going to divide both sides by 2. So we're going to get 3 to the x over 7 power is equal to 0.2. And here's where, once you've isolated the exponential expression, this is where you ask yourself if you can rewrite both sides with the same base or not. But no, definitely not. 3 is not a power of 0.2. So we're going to use the other technique, which is to take the natural log of both sides of the equation And then that means we can bring our power out front. So we have x over 7 times the natural log of 3 equals the natural log of 0.2. Remember, the natural log of 3 and the natural log of 0.2, these are just numbers. They look weird, but there's no variable in them. So this is a number. So we're just going to divide both sides by that number. Okay, so that's going to give us x over 7 equals natural log of 0.2 over the natural log of 3. And then we still need to multiply by 7 to get x completely by itself. So that's going to give us x equals, anytime you multiply a whole number times a fraction, the whole number is going to go into the numerator, the top. So we have 7 times the natural log of 0.2 over the natural log of 3. This is your exact solution. Okay, but we were also asked to estimate it, so let's go ahead and get an approximation using a calculator. So we're going to have 7 times, and then the natural log of 2. Okay, and then we're going to divide, let me say equals, so that's what's in the numerator, and then we're going to divide that by the natural log of 3. And so we get about negative 10.25. So x is approximately negative 10.25. Now you might be wondering, hey, Ms. Hearn, you said you can't take the log of a negative, but we're not. When you put that negative into the exponent, it's not saying that the number is a negative. It actually has the effect of just making it into a fraction, right? Negative exponents really just mean it's on the wrong side of the fraction bar. All right, let's look at this next one, part E. 7 to the 2x plus 1 equals 3 to the x plus 1. So, or x plus 2 rather. Sorry, I'm getting a little distracted because the stream health is pretty bad. So we have two exponential expressions with two different bases. We cannot write them as the same base because 7 and 3 are both prime numbers. They're not going to be powers of the same number. So what we're going to do is take the natural log of both sides. And the whole reason for doing this is just so that we can get those variables out of those exponents. So we apply the power rule of logarithms. We bring the 2x plus 1 out front. So we have 2x plus 1 times the natural log of 7 equals x plus 2 times the natural log of 3. Make sure that you put that power in parentheses because the whole thing is being multiplied by the natural log of 3. And then we're going to do something a little unexpected probably. So you'll notice that the x that we're trying to solve for is on both sides. And it looks kind of weird because we have these parentheses and the natural logs. What you want to do is kind of pretend like this is a formula. And we're going to solve for x. Think of the natural log of 3 and natural log of 7 as almost being like other variables. So what you would do when you're solving a formula and the variable you're looking for appears in more than one place is you would distribute through any parentheses first. So that would give us 2x natural log of 7 plus natural log of 7 equals x times the natural log of 3 plus 2 times the natural log of 3. And so now we have 4 terms and 2 of them have x in them. So we want to get the terms that have the x to one side and the others to the other side. So I'm going to subtract x natural log of 3. And I'm going to also subtract the natural log of 7 from both sides. Okay, so that's going to give us 2x natural log 7 minus x times the natural log of 3 equals, and then over here we're going to have negative natural log of 7 plus 2 natural log of 3. Okay, so the x's that we're looking for, looking to isolate, are on the left. So now this is the trick, you factor it out. So you have, it's the same every time when you have a problem like this. Get the x terms to one side and factor out that x. I'm actually going to write this as 2 natural log of 3 minus the natural log of 7. Just one less symbol to write. Okay, and then the last step is the same. You're going to divide both sides by whatever this stuff is that's being multiplied by the x. All right, so x is equal to 2 natural log of 3 minus natural log of 7 over 2 natural log of 7 minus natural log of 3. Now, this is the exact solution, but if you want a decimal approximation, you're going to have to plug this into a calculator. And when you do that, remember that this fraction bar is acting as a grouping symbol, so there are implied parentheses here. So you have to watch out for your order of operations. The calculator is not very smart. It depends on you to tell it what the operations are. So you will most likely have to put these extra parentheses, and calculators often automatically require parentheses around logs. So you might have a lot of parentheses when you plug in. I'm going to leave that one for you to do. And we're going to move on and talk about logarithmic equations. So again, we have a couple types of logarithmic equations. One is the type where you can have a log on one side and a number on the other. And the other one is where you can get it to look like a log equal to a log. So let's look at an example here of when you have a log equal to a number. Remember, you might have to rearrange to get to the point where you have a log equal to a number, but once you do, all you have to do is use the definition of a logarithm, or in other words, converting the log to exponential form to solve the equation. By the way, it's a logarithmic equation. What tells you it's a logarithmic equation is that you have an x inside of the argument. So here's an example of a logarithmic equation. We have an x inside the argument of this logarithm. And so we need to isolate the log so we can get it into the form of a log equal to a number. So I've subtracted 2 from both sides. So we have log base 2 of 5x equals 3. And then this is the key step here. This is the key step, converting from logarithmic form to exponential form. Remember, identify the base and the exponent. So we have 2 to the third power equals 5x. You can also write it as 5x equals 2 to the third power. The order doesn't matter, just as long as you have that 2 to the third equal to the argument of the log. Okay, now we're going to not leave it as 2 to the third. We're going to write it as 8. So we have 5x equals 8, which we can solve by dividing by 5, and there we go. Now, there is a check step that's required for logarithmic equations. It is possible that we make an assumption that's an incorrect assumption that causes the argument of one of our logs to be negative. And remember, we can only take the log of positive numbers. We can't have 0 and we can't have a negative. Which is not to say our answer can't be 0 or negative. What that means is that, for example, in this case, the argument was 5x. So if I plug in 8/5, do I still have, oops. It's not working. Let me just do this. Equals 5 times 8/5 which is a positive 8. That's greater than 0, so then we know that our solution's going to work, as long as we didn't make any other errors. So you don't have to check the whole thing. It doesn't hurt to plug in and see if you get a true statement, but what's absolutely mandatory is that you do at least check to see that the argument is greater than 0. All right. The other type of equation we said is where you can rewrite it to be in the form of a log equal to a log. Here I actually have an equation, a log equals to a log plus a log. But remember, by the product rule, we can combine those. First, we have to bring the 2 inside the log, so that becomes log x squared plus log 5. We just condense the log here to log x squared plus log of 5, and then we're going to use the product rule to condense it further to 1 log. It's going to be the log of 5x squared. So now we have 1 log equal to 1 log, and we can use the one-to-one property of logarithms this time. So if you take the log of a number and it equals the log of another number, then those had to have been the same numbers. This is assuming, of course, the same base, but when the base is not written, it's assumed to be 10, so we have the same base. So you can just drop the logs and get x equals 5x squared. Now this is a polynomial or quadratic equation, so you have to get it in standard form. 0 equals 5x squared minus x. And you can use factoring in this case pretty easily to solve it. Factor out an x, that leaves 5x minus 1. If you set x equal to 0, we get a 0 answer. You set 5x minus 1 equal to 0 and solve, you're going to get 1/5. But again, checking that the argument is positive is a mandatory step. And if you notice, our arguments are x and 5. 5 is okay no matter what, but x is dependent on what we pick for x. So if x is 0, that would cause our argument to be 0. And our argument cannot be 0, so we have to throw that out. But our argument can be 1/5. That's still greater than 0, so we're good there. So the only solution to this equation would be 1/5. All right, so those are the 2 different types of methods for solving logarithmic equations, right? We can use the condensing properties to either get log a number or log equals a log. So let's look at a couple of examples. It says solve each logarithmic equation using one of these 2 approaches. Be sure to reject any value of x that is not in the domain of the original logarithmic expression. In other words, throw out anything that causes your argument to be 0 or negative. Then it wants us to give an exact answer and then estimate the solution to 2 decimal places if necessary, so if appropriate. All right, so here we have log base 5 of x minus 7 equals 2. Okay, it's a log equals a number scenario. So we're going to rewrite it in exponential form. All right, so remember how we read this out loud is log base 5 of x minus 7 equals 2. So we know that 5 is the base. And then when you take the log of something, what you're calculating is the exponent. So 2 is the exponent. So that means we have 5 squared, and then the argument has to be whatever the third number is, whatever's left. So 5 squared has to equal x minus 7. So that's how I go between exponential and logarithmic form. That's something very important for you to practice. Okay, so now go ahead and square that number. So that's 25 equals x minus 7. Now we isolate x. It's a regular old linear equation. We can just add 7 to the other side. So we get x equals 32. Now we have to confirm that the argument is positive. Is the argument greater than 0? So the argument is x minus 7. If I plug in x equals 32 to x minus 7, I get 32 minus 7, which is 25, which is definitely greater than 0. So that means that we don't have to throw out our solution. X equals 32 should be just fine. Remember, you can ask me questions by typing into the chat bar. And we're going to move on in the meantime, but I can always go back to that problem if you have a question about it. All right, the next one we have is 5 plus 6 times natural log of 2x equals 35. All right, this doesn't fit either the form of a log equal to a number or a log equal to a log yet. But I can easily isolate natural log of 2x, right? I can subtract 5 from both sides, so that would leave me with 6 natural log of 2x equals 30. And I can divide both sides by 6. And that's going to give me the natural log of 2x is equal to 5. All right, now the log equal to a number form is what we have, and we want to rewrite it in exponential form. But to do that, you need to remember that the natural log really means log base e. So we have log base e of 2x equals 5. So the base is e, and we take the log, we get the number we get is an exponent, so the exponent is 5. So we have e to the 5th equals whatever's in the argument, 2x. Okay so far? All right, so then now all we have to do is divide both sides by 2. And we get x is approximately, no, not approximately, x is exactly e to the 5th over 2. If we wanted a decimal approximation, we would have to plug that into our calculator. Let's see what we get. We have, I have to find my e to the x key, which on this calculator I have to go big here. So, I want e to the 5th, which is 148.4, and then divide that by 2, and we get about 74.21. Oops. Okay, so that's an approximate answer, and then e to the 5th over 2 is the exact solution. So when they ask you for that in my math lab, that's what they're asking for. Okay. Part C, we have the natural log of the square root of x plus 4 equals 1. And what do I always tell you in class? When you see a square root in a log, change it to an exponent. So this is going to be the natural log of x plus 4 to the 1/2 power equals 1. And we're not going to bring the 1/2 out front because I want to just go ahead and rewrite this in exponential form. This is log base e, because it's natural log, of x plus 4 to the 1/2 equals 1. So we're going to identify the base and the exponent. The base is e, and the exponent is 1. And then the argument is what that's equal to. So we have e to the 1 equals x plus 4 to the 1/2. Okay, now what do we do? Well, we're going to square both sides to get rid of the 1/2 power. So, because remember, when you raise a power to a power, you multiply the exponent. So if I multiply 1/2 times its reciprocal, 2, it's going to turn into a 1. And that's what we want. So we're going to have e squared equals, and then we're going to have x plus 4 to the 1st power. But anything to the 1st power is itself, so I really don't need those parentheses. I can just say e squared equals x plus 4, and then I'm going to subtract 4, and x is equal to e squared minus 4. If I want a decimal, that's the exact answer, exact solution. Okay, you can't write it any other way. I mean, there are other ways to write it, but they would all involve e. But if we want an approximation, we can just plug that into our calculator. So let's find e squared So I'm going to raise e to the second power. And then we're going to subtract 4. And we get approximately 3.39. Okay, and we should check to make sure that our, oh, and I forgot to check in part B, I think. We'll go back to that in a minute. All right, you need to check to make sure that your argument is not 0 and not negative. If you plug 3.39 or e squared minus 4 in here, you're going to see that you get a positive number. You're adding a positive to a positive, so we're good to go. So these two will work. In the previous question, part B, same thing. I should have mentioned that if you plug 74.2 into 2x, the argument, you're going to get a positive. So that worked out too. All right. Of those forms, but we should be able to use condensing to get it into one form or the other. Since we only, there's no log on the right-hand side, then we need to get it in exponential form, identify the base, identify the exponent, right? And then what's left is going to be the result. So we're going to have 2 is the base to the third power equals x squared minus 1. Having trouble scrolling, sorry. Okay, there we go. So that means that we have 8 equals x squared minus 1. This is a quadratic equation. I'm going to get it in standard form. So 0 equals x squared minus 9. That is actually easy to factor, so let's just stick with factoring. X minus 3 times x plus 3. It's a difference of squares, right? So it factors into conjugates. So we set each conjugate, I'm sorry, yeah, that would be true, but each factor to 0. And we get either x is 3 or negative 3. And then we have to check to make sure that in our original 2 arguments that neither of these causes us to get 0 or a negative. And unfortunately, if you plug negative 3 in here, you're going to get a negative 4. And if you plug it in here, you're getting a negative 2. So it does cause a problem. So we cannot include negative 3. However, if you plug 3 in, you're going to get 2 and 4, which are positives greater. So we can't use the negative 3, but we can use the 3. All right, and this will be the last equation for today, and then we're going to go offline. So log of x plus 7 minus log of 3 equals log of 7x plus 1. Again, we either want a log, first option, a log of something equals a number, or we want to rearrange it so we have a log equal to a log. All right, so in this case, since we have logs on both sides of the equation, I think that we can use the condensing property on the left, and then we'll have log equals a log. This property that we want to use, since we have subtraction of 2 logs, we're going to use the quotient rule, which says that if you have the difference of 2 logs, that's the same as the log of the quotient. So we're going to rewrite this as the log of x plus 7 over 3. Be careful, this is not log of x plus 7 over log of 3, right? It's one logarithm. We've condensed it from 2 logs down to 1. And this is equal to log of 7x plus 1 according to the original equation. Just bring that down. And then now we have the log equals a log scenario, and that's a nice scenario because then you can just drop the logs and get x plus 7 over 3 equals 7x plus 1 and solve in the usual way. I'm going to clear the fraction by multiplying both sides by 3. X plus 7 equals 21x plus 3. And then we're going to subtract 1x and subtract 3, and we get 4 equals x. Oops. Hold on. 20x, I mean. Okay, so we're gonna subtract x, subtract 3, subtract 3. We get 4 equals 20x. Divide both sides by 20, x equals 4/20ths, or 1/5. Okay, and of course we need to check to see if this is okay in our arguments, but notice that our arguments x plus 7 and 7x plus 1, they only add to the number if they don't subtract, so it's not going to make it a negative. So this one's going to keep all of our arguments positive and we're good to go.